Okay, hello and welcome back to another lecture of the missing semester 2026. Today we're going to cover the topic of packaging and shipping code. And what that refers to is the idea that while you might get code to work in your own computer, it might not be trivial to run the same code you're running in your computer into a different computer. And while in theory this sounds simple, just like copy whatever code files you wrote in your computer, copy somewhere else, and try to run the exact same thing, this actually can be quite hard. The code you write not only relies on that, but there's an entire set of dependencies that you implicitly have. So things from the programming language runtime or even features about your operating system might prevent the code that you wrote running in a different machine. This will depend quite greatly from language to language, and also will depend on the type of program or application that you're developing. It's not the same to just write like a simple Python library than say build like a CLI tool or even a full-fledged web service. All those things will require different dependencies and environments. But there's like one common theme across all those things is at the end of the day, you're producing an object that someone else can download. And we usually refer to that object as an artifact. And with that artifact and the assumptions that artifact makes about its environment, we should be able to run it and get the same results. So the first thing that we're going to cover is the notion of dependencies. To see an example, if we have this code, this is like a very, very small Python program where we're importing the request library, which allows us to make HTTP requests, and we're trying to download the course website. And as we try to do that, we can find that it actually doesn't work. And the reason why it doesn't work is actually told to us by the programming language runtime. The request module doesn't exist. The request module is not part of the default installation in Python. It was implemented by someone else, and we need to get that code into your computer in order to use it. In Python, the tool to do this, by default, the one that ships with the programming language runtime is pip, and we can do pip install requests to tell that we want to download this dependency. If you look here, there's a lot of things that just printed in our command line. And what is going on is that when we ask to get the request package, we went to the Python package index and asked, like, is there like a request package there? Can this be installed? And we can see here that this request is here, and the Python package index like stores all the information so that you can install it. But before you can install the request package, you can see that we're downloading other libraries as well. Those are the dependencies of requests. Before we can pull requests and install it, we have to recursively go through all the dependencies of requests, and the dependencies of requests, we have to like navigate this entire tree and install them in order in our file system. Now we can check that the program runs, because now it has the dependency and it was able to execute that code and download the website correctly. 200 here is like HTTP code for everything went well. And if we say, is request installed? Yeah, we got request. We got the latest version of request, which is the one listed in the package index. We can actually also check where request is in our environment. In Python, you can actually check where this is. And we can see that this got installed in my default Python installation, and thus kind of where all those files that we downloaded from the Python package index were unpacked. Now, this process is like this for Python, but will change from language to language and from environment to environment. And not just in the exact program that you will be running, like in the Rust language, you might be using cargo. It's not just a change of program, but also different programming languages come with different approaches and different philosophies. So for instance, in Rust, we have cargo, and cargo is like a unified tool. It will do pretty much everything. It will do the compilation, it will do the packaging, it will do the publishing. It's like a pre-unified toolchain, whereas in Python, actually the unification happens at a specification level. The Python languages is like, these are the rules, and it's up to you to write like any tool. So we will see that pip is one tool that can do this job, but there are other competing tools that just speak the same rules. And there are even more extreme cases, like if you've ever installed LaTeX in your own computer, you will find that there are installations of LaTeX that come with actually thousands and thousands of packages. It's really rare for you to have to install a LaTeX package because all of them just come bundled with the language, because that's a reasonable model for LaTeX to assume. Now, as we start requiring more dependencies, the challenge is we might run into dependency conflicts. So, for instance, we can say that we want to install these two libraries, and we can say like, we can constrain the versions, and we can say like, okay, we want the NumPy version to be greater than 2.0, and then we actually have like a sibling library of NumPy, and we want it to be less than 2.0. And if we try to execute this, we get a lot of information, but the summary here is there's no set of versions here that is compatible with one another, because kind of the typing one requires the NumPy one to be less than 2.0, and as you start adding more packages, this is more of like a pathological example, but as you start adding more packages, you might run into this situation of having it being impossible to harmonize all the Python packages in your operating system. The solution to this is dealing with environments. The way we can create an environment in Python is the syntax. By executing this command, what Python is doing is creating a replica of the language runtime that is completely kind of brand new, isolated. And if we activate the runtime, then we can check what our executable Python is, and now it points to a different place. Now it points to this brand new folder that we created that is called myenv, and that also applies for other binaries related to the Python runtime, say for example pip. If we check whether we have that request package that we recently installed, it's not here because we installed that kind of at the default installation. Now this is an isolated one. We can still install it. We can install requests here. And it did pretty much the same process of solving all the dependencies. And if we pip list, now we can see that along with the default setup tools and pip, we have now all those dependencies as well. And going back to where request is installed now, is installed its own isolated environment. And in general, it is really good practice to have like a per project environment for you to put your dependencies in. As like you start working on more projects, it will be easier to keep track of like the exact set of dependencies and not run into what we usually call dependency hell, which is when you start getting lots of different dependency conflicts and they're like really hard to resolve. Now, as I said earlier, the Python packaging landscape is quite elaborate. It has evolved over the years, and there are multiple tools that implement kind of the same packaging logic. At this day, the easiest one to work with is UV. It's kind of like a holistic replacement of not just pip, but like a few different tools. And we will use it in the examples going forward. Is much more user-friendly, and I think like the most remarkable feature that people usually highlight is that it's way faster than like pip in many instances, not just at installing, but doing dependency resolution and other things. It can also handle creating virtual environments. So we can create another virtual environment, and here, I think we didn't delete this one. We're going to delete it. We can create a virtual environment. Now, again, a virtual environment is nothing magical, just another folder that has a bunch of files that correspond to a Python installation. When we do this source command, we're just changing or path another environment variables in our cell, so Python can actually resolve to this other option. And here we can check that there are no packages, and if we install requests, we can see that UV does exactly the same job, but it's actually much faster. And as you start getting into bigger and bigger packages, it can go actually from minutes to seconds. That's like how fast it can get. Beyond isolating dependencies, another common pattern that you'll see not only in Python, but in other programming languages, is the idea of isolating language runtime versions. So in this computer, we have 3.11, and when we're creating these environments, we're also getting the 3.11 version. But if we need a different one, because maybe the project that we're working on uses 3.12, then this can be done. You can create like a virtual environment with a different Python version. And if we now activate it, we can check that effectively the version has changed to 3.12. So it's another part of like the dependency isolation story. Any questions so far about packaging? No? All good? Okay. So the So far we've seen how other people create packages and how we can like include those packages. Now the question becomes, if I have some Python code, how can I make that possible to install by other people? The default pattern that you might have seen is if I have file like green.py, it's nothing crazy, just the most simple hello world command. If we, within the same folder, we say from greeting, and then I think we can, we do this, we haven't quoted that. It works, and that's because Python by default, it tries to look for like any matching green.py in the folder we're running things into. But if I now change folders and I try to do the exact same thing, then it doesn't work. Python doesn't have a way of finding this greeting package. It's not part of the installation that we have. In order to make the package installable, we need to follow the rules in Python. So we had an example of how to do this. So here on the right is pretty much the same code, except we've added a way of also running it with a command line tool. So the idea with Typer is it allows us to do this, and it works. So it's like it's similar to the default library argvars, and it's just useful for us to introduce the notion of a dependency. And here on the right, it's the pyproject.tomo. This is the kind of the rules of the game. This is how Python tells you if you want to create a package that people can install, you have to create a file with this specific schema. There are kind of more, there are other ways of doing this that you may have seen, like requirements.txt, setup.py. Those also work, but going forward, the recommended way is this way. So here we have, say, kind of what is the name of the package, like when we install it, how Python will be able to find it, what version it is. This is useful for kind of constraining versions, some description. Here we're saying we're declaring our dependencies. We're saying this library cannot be installed if you haven't installed typer with greater or equal than 0.9 before. This just specifies the build system that is used to create the artifact. And then this tells Python, when you install this, on top of that, also create like a greet program that can be resolved and that calls this CLI function in the greeting file. So now with all of that, we can actually UV pip install this folder, and it kind of resolved the entire thing, and it built it. And now if we go here and we try to do that same idea of trying to import, wait, that to have work, are we, probably because source reading. Yeah, okay. I had not activated the environment. So now we have activated the environment that actually has made it installed not just our package, but also all the dependencies. And now if we go anywhere and we try to import, now greeting resolves. Greeting is a package. We can actually list the packages and search for greeting in like greeting package has been installed with 0.1. And on top of that, now we have the greet command available. And that's because kind of we have now built this package from like the source file that we had in this folder. This is great, but this will mean that if someone wants to install this package, they will need all the files that we have. In practice, when we're dealing with software packaging, there is usually a difference between source code and kind of like pre-built artifacts or pre-built binaries. Kind of source code is just like kind of like the raw instructions of how to kind of build everything. But in order to use that, you need probably an entire like tool chain of dependencies and like third-party libraries. But in practice, in order to run that program, you might not need as much code. A good example of this is if we go to the grep tool that we saw in an earlier lecture, we can see that they have like a releases page. And in this releases page, they actually have a lot of pre-built binaries for you to download. Like if you just download this program, this is a program that you should be able to execute in your computer. The caveat being here that when you pre-build the software, now there might be limitations on what platforms can run that software. The two most common aspects that you will see are the operating system that is running under and the CPU architecture. So that's why there are, instead of being just one file here, that's where you're seeing a lot of different files. So it's not the same running this for like a Windows PC that it is for like a Mac OS running on Apple Silicon, or even like Linux with a Raspberry Pi. Each one of those will need like a specific binary for their architecture. Going back to the Python story, the way we build an artifact that people can use is creating a wheel. Wheel is just the kind of format, and when we do UV build, a lot of things are getting produced, but Python is packaging our application in a standardized way so that like pip and UV and all these tools can actually manage it and install it correctly. They has created two files. The first one has the source code, and the second one is this wheel file that if we give to someone, this individual file, they can run UV pip pip install, sorry. And if you do this, we have now installed the same library, but from that single file. And one thing to note is this wheel file is not magical. In the case of Python, it's just a zip folder, and this because we have a pretty minimal package. This zip folder just contains the greeting file that we created along with some metadata files that the package manager requires. Now, as you start building your libraries, you start adding more and more dependencies. So one challenge is in order to specify your dependencies, you need to know that they're going to work with your code. The way we do this in software packaging is by specifying kind of different kind of version ranges of what works and what doesn't. Again, the syntax will maybe vary slightly from language to language, but we can say things like, we want this exact version, or we can say things like, we want a version that is at least this, or even more constrained ones. We can say like, greater or equal to this, but never get to 2.0. And people, when they release new versions, right, like you're not installing from the latest, you're usually installing from something that is kind of known and stable. If we go back to that RipRep example, they released this like 15.1.0, and they're saying what changed, and they're saying there's like a bug fix, and there was like some new feature announced. This is called a change log. That's like how people report what has changed from the previous version, so you know that it's fine to upgrade or not. And in principle, you could just look at the change logs of all the dependencies that you're working with. The challenge is, again, it's not just about your dependencies, it's about the dependencies of your dependencies of your dependencies. So even in our minimal example, we can use UV tree to see what is the tree of dependencies that we created by just adding typer. Like if we kept track of typer, we might think it's fine, but it's actually depending on a lot of other libraries. So what software developers do is create conventions about like what happens when you increase a version in one way or another. The most popular convention is called semantic versioning. Under semantic versioning, versions have three numbers. They're all just natural numbers, or like positive natural numbers. And the idea is you have a major, a minor, and a patch versions. And they define what has changed from the previous version. Whenever you upgrade the major, you pretty much provide no guarantees. Like something that was working before, if we upgrade major, might break. And that's why you might see those examples where like you prevent the major version from changing. If we upgrade the minor version, we're saying, oh, there are new features, but everything that was working before should still work. Now it's just these new features are only available in this version. And when it's just bug fixes and maybe documentation changes, you usually just do like a patch. It's just like everything is exactly as before for like the users of this library. And if we go back to this RipRep example, we see that RipRep actually, like a lot of libraries, follows the semantic versioning. And they went from 15.00 to 15.10 because they added this new feature. Now, the follow-up to versioning is when you're building an application, there is a tension between specifying all the versions. There is a tension between specifying all the versions exactly. That means that now someone will install exactly the same version that you use and there won't be any issues, and just providing ranges. Saying like, okay, hopefully it works with all these different versions. There's like an important distinction here. It depends on the type of program that you're building. If you're building a library, say for example, we're building the requests library in Python, we actually want to follow this approach of having like a wide range of values. And that's because people are going to install requests along with many other libraries. So if we put really strict requirements, that will probably run people into dependency conflicts and they won't be able to install our library with other libraries. And we can see this in action if we just look at how request specifies its dependencies. There's actually pretty wide ranges that they specify, and for the most part, they just constrained on major just in case. That's not the same if we're, say, building an application that people are going to use. There's no advantage of just providing these wide ranges. We want to pin everything so that we know that whoever uses our final product just gets like a reproducible experience. So if we look at the dependencies of RipGrep, we can see that RipGrep provides no ranges. It's like exactly each version of the RipGrep dependencies has to be used to build the tool because they have tested that these versions work. And the follow-up to this is as you start trying to make your packaging more reproducible, you will see that people not just specify the kind of the versions, but they try to provide a more thorough approach on specifying pretty much everything. So here we can look at a file that was generated by the Cargo Package Manager that not only resolves the kind of dependencies, but also the dependencies of the dependencies, and it has the exact versions for each one of them, along with like a checksum of this library. So it's not only like, okay, this version is like when we downloaded it, this file had this exact hash. And we can do the same thing in Python. So if we go to our greeting package and we do uv log, this will create a log file. And this log file contains a lot of metadata. It's intended for machines, not really for humans, but we can inspect it. We can see, for example, that the typer dependency, we said that had to be greater than 0.9. But when we created this reproducible setting of our package, it used the latest one. It used like 0.21.1. And not only that, it actually downloaded both the kind of source and the wheel. And here we have information about where it was downloaded it from and what was the exact hash that the file that was downloaded used. So now if anyone uses this UV sync, they will get the exact same versions. Like if they were using pyproject.toml, maybe now there's like a newer version of Typer, they will get that one. But if they use UV sync, they're guaranteed to get the same set of versions that we got when we were testing the application. There are limitations to this, obviously. So far, like as with most things in packaging, the moment you leave the boundary of your programming language environment, you have to start using tools that are intended for kind of wider dependency management. For more complex management, there are package managers like Nix that not only handle, say, Python, but they actually handle all the packages that you could install, and they provide like a reproducible way of pretty much doing everything in your operating system. And that's because you might think that it's fine to just build Python 3.12 as long as 3.12. But Python requires a C compiler, and the version of the C compiler can be different. So this is a way of just managing like every single bit of variability in your computer. And there's actually like an operating system that is based on this idea as well, that where you will trade like flexibility for complexity. But it's good to know that in cases where reproducibility matters that much, there are tools that you can leverage. Now, getting into this topic, the follow-up is, as we start depending on things that are outside of like our programming language runtime, say like for example in Python, if we want to start using dependencies like say like a GPU driver, like here in this case there's like this QPy library, and QPy is like a Python layer to like a Python wrapper to call a bunch of CUDA, like NVIDIA instructions that Python cannot really manage. And actually, if we go to the installation instructions of QPy, instead of saying just like pip install this, they're going to say, oh, you have to have like a compatible CUDA toolkit. And now it's impossible for us to just specify this as part of our Python packaging. We have to go kind of one level above. And if we look at how they package their Python wheels, we see the same pattern that we were seeing with RipGrep before, where with RipGrep we just had the operating system and the CPU architecture. We still have those, so we have like, say, for example, Windows and AMD64, but now QPy, because it's tied to a lot of the features of Python and CUDA, they have to compile separate version for, say, different CUDA runtimes. They have to do for different versions of the Python, so for example, Python 3.12, Python 3.10. And you need to find the right artifact in order to install this library. To avoid a lot of that complexity, what we really want is to zip with our artifact pretty much everything that the user could ever need. The challenge is that might mean zipping the entire computer. And how do you zip like an entire computer? Well, traditionally, that's kind of what people started doing. They virtualized computers. They created this idea of just running computers within computers with some constraints, but for the most part, you could just do it. You could run Linux within Windows and vice versa. And that meant that if I gave you like a virtual machine image, you could just execute it and it will have all the dependencies that your program will require. The downside of virtual machines is there's a lot of overhead. Like you're running an entire operating system within your machine in order just to get an application running. So to try to trade off that complexity, what developers realize is, for the most part, applications only care about their kind of user level dependencies. They don't need to modify the operating system itself. So what you can do is you can reuse a lot of the core components of the operating system and then have the application layer be actually what is isolated. And this is the idea behind containers. They're only supported in some operating systems. So Linux and BSD actually support it, but you don't have really this notion in, say, Windows. And when you want to run containers in Windows or Mac, what actually happens is you run a Linux virtual machine and then you run containers within it. But that's fine, because actually when you go to a lot of kind of applications that are deployed in production, they're just using Linux, the different flavors, but still all Linux. And more we're seeing this container pattern. There are different containers implementations. As with most things, the tooling changes from one to the other one. The most popular at this point in time is Docker, and Docker relies on a container runtime called Containerd that other tools are compatible with. So if you've ever heard about Kubernetes, Kubernetes speaks the same language of how a machine is defined, and that's useful because Kubernetes has a lot more features like fault tolerance, but we can reuse the same images. So it's a lot of talking, very abstract concepts. What does this actually look in practice? Well, in practice, you will install Docker, and that spawns a process that allows you to kind of reuse this part of your operating system for other containers. And if we do we do Docker run, and we do Python, and we do this, we're saying this has to be interactive. Now, this looks like we're just running Python. This is like I can do whatever I'm used to doing. But it's actually different. This 3.14 Python is running within an isolated container in my machine. It's not an environment. It's like an entire machine that is being isolated here. On top, instead of Python, we can actually look at Bash. And if we look at Bash, we can inspect the file system. We can also check what processes are running. And because the containers don't have all that overhead of doing all the operating system bookkeeping, here there are no processes. It's just like PS and Bash. It's just whatever processes you spawn are the ones that are actually running. And Python 3.14 is a valid container image, because if we go to Docker Hub, someone has built this like official image that is some Linux. We can verify which Linux. Actually, we can just say, oh, it's a Debian installation. It's a Debian. Debian is like a Linux distribution, and they have installed a valid Python runtime on top. If we needed, say, a different toolchain, we say needed Node, then same idea. You download you tell Docker to download the image, and here I have already downloaded these images, not to slow down the lecture, but we can check what images we have, and we have like a few images. All of these were downloaded from the Docker servers, and I only have to download those files in order to be able to run these like virtual computers within my own computer. The question is now, okay, but how do I build my own image? Like, it's fine having Python image, but that's not that useful because I want to package my entire greeting library. So for that, we use a special syntax that is the Docker file syntax. This might look like Bash, but and every command kind of looks like that. But in practice, it's a different language that is designated to create Docker images. So here, for example, we're saying start from the Python 3.14 image. So it's like this is the starting file system that we're going to have as a starting point. And then we install UV. We maybe need the C compiler in order to build some things. Then we copy the files that we need for our library. And we actually, at the end, we have to install it, because otherwise we won't have, the package won't be installed within that virtual computer. And in order to produce a valid image, we use a syntax like this. We're pointing it to the folder that contains the Docker file, and we're saying we need to give it a name. We have to say, okay, this is the greet image. So then later we can refer to it. And here it's actually reusing a lot of the steps, but you'll see that there are like these numbers that are being created. And that's because every single of those commands is getting tracked by Docker. And it's creating like layers of like changes to the file system so that then they can be reused. And if different images reuse the same layers, it can actually deduplicate that work. Now, if we run, so by default it's getting tagged latest. We always need to give it a tag. We didn't give it a tag, so it used latest because that's the convention. And since we installed our package that define the greet tool, and the greet tool is findable because we told Python where to find it, then now what we did is very quickly, like we spawned this virtual container that has this file system including our package, and then we executed this tiny greeting program that we created. Now, it might be tempting to just use a syntax like what you're used to do in shell scripts, but Docker files have some caveats. There's like a learning curve to them, and in practice, they end up looking a bit more like the thing on the right. And that's because here, every single step is creating one of these intermediate layers, and we want to reduce as much as possible this layer. So we have this like apt update to just download the latest versions for the system package manager. But here we combine these operations, and we also give some special flags. So like, don't keep extra bookkeeping stuff. Like, we don't need it. We're not going to install anything else. This is a final product. And the same for UV. Like, don't try to save any caches here. The caches are not going to be useful because this is like a final image for people to use. But the same thing applies. We can build that optimized image, and because I did this earlier, everything has already been cached by Docker. And now if we run it, things to be, so it'll be able to find, there we go. Same thing works. The difference though is that if we list the images and we compare the greet versus the greet optimize, the first one, because we were just downloading all the files, not trying to save any space, we produce an artifact of close to 2 gigs in size, whereas the optimized one, following those patterns that you'll encounter in the wild, that one had like just half a gig of size. And I'm sure there are more things I could have done to make it even smaller and easier for people to run and deploy. Any questions so far?
How do you know what are like all the things that you need to put in your Docker file? Like, when you showed us the Docker file, like, have you created that by hand? Have you used a program?
Yeah, the Docker files are. Oh, sorry. So the question is, how do you know what to put in your Docker file? Like, is that created by you or is that created automatically? So, using the simple one, just for simplicity, Docker files are not created automatically. Like in the large majority of cases, you write them by hand, and the process you have to figure out what your program or your application needs in order to function. And here we actually probably didn't need the C compiler. Like, we could have simplified this to copying the source code of the app that we were deploying and then installing. I just was adding that as an extra so that there are like some conventions on how to do Docker files when you're installing things and cleaning them. In practice, if our application, for example, if our Python package had C extensions and we had to compile those C extensions, then that will be part of the requirements that we needed, and then in that case we will have to use GCC. It will be pretty obvious to some extent what you need to put in your Docker file. Like as you start like using your application and figuring out like your dependencies, you will quickly realize like, oh, my application cannot function without this thing or that other thing. Going back to the QPy example, we know that QPy requires CUDA. So either we start with an image that gives us CUDA, or then we need in our Docker file to install it somehow, because we know that our application requires it to function. Now, the running containers is good, but then at some point you will start finding like another layer of abstraction. And the following layer of abstraction is, instead of relying on dependencies that are just like regular packages that you can say like import requests and use it, you might start depending on entire services. And those services have their own separate container. So as an example, this could be a database. Like maybe you're using an entire PostgreSQL database, and now you have to decide, like you have the option of trying to install Postgres within your Docker file and hoping that the dependencies that Postgres has and the dependencies that your program has don't conflict with one another, or you have to just separate them into different containers and make them communicate with each other. And because dependency hell is a very real thing and kind of harmonizing versions can be quite complicated, that second pattern appears substantially more often. So if we want to, say, create like a web application, really simple one, where every time someone visits, we're going to say, okay, this page has been visited this many times. We could, of course, save this to some file or wherever, but it's more fun if we actually put like a real database that we are deploying, and especially one that gives us some good properties. So in this case, we're going to use etcd, which is fault tolerant and like kind of like pretty robust database choice that we can use. But since it has like some requirements, it could be difficult to install along our application. So instead, what we're going to do is we're going to communicate with it through requests. So here, whenever anyone visits our website, we are calling this helper function of increasing the visit counter. And if we go to see what that does, we're saying, oh, okay, there's some overhead because we have to encode and decode. But the important thing is we're making requests to this URL with a specific payload. We're saying, okay, get me the key value, then we increase the key value, and then update the, like, put that key with that new value. This is just like most simple database operation we can do, just like read and write increasing one. But now we have a problem. Now we have to deploy these two containers and make them talk to each other. We could do this by just doing a bunch of Docker run commands. We will have to also learn about Docker networks and how to kind of make them be in the same network. But in practice, what you will see is some way of having another programming, like a dedicated programming language just for specifying how services have to be deployed and connected to one another. So Docker Compose is an extension of Docker that does this very same thing. Like, it takes in a configuration file and it translates it into a series of Docker commands to deploy the containers that you need to run. In this case, we're deploying two services. So we're deploying our web service, and then we're deploying our database. And we're here saying, okay, this is the image for the database. For our application, we have like a Docker file here, so we use this different syntax. But one thing I want to highlight is, for example, we can specify a dependency. Like, we should not start the web service before the database is running. So that could be quite tricky if we were to do this manually. Here we do it in a declarative way. And it's fairly easy for us to say, don't start this until this one here is running. Also, we need to give some configuration. Beyond kind of like packaging the code, you also have to think about how people are going to run the code and how they're going to modify its behavior. A good mental model is the same application should be able to get deployed in 2 different machines, only changing configuration files, never the source code. The source code should not be modified if you're just changing, for example, what port you're going to listen on. So specifying configuration comes in different ways. We already saw this in the scripting lecture, and a few of the patterns that we were seeing there reappear here. So our program, for example, expects the URL of the database under this environment variable, etcd URL, whereas for etcd, it's easier to pass the options as just like CLI flags, and that's how we're specifying them here. Now, if we do Docker Compose app, that's spawning both containers, and we can see this in the logs where we have the etcd container and we have our web app container, and it says that it's running under this URL. And if we query that URL, we get that this page has been visited 1 time. If we visit it again, 2, 3, and so forth. But like every time we're making a request to the web application, the web application is communicating with the database application in order to update these counts. And we have now solved the problem of how to kind of deploy these more complex multi-service applications. We still have the problem of who starts this. Like, I cannot just hope that like every time this machine gets restarted, someone SSHs in and does Docker Compose app. So another kind of pattern that we'll see is like ways of orchestrating services starting. In Linux, the most popular one is systemd, and systemd has a way of defining services. We can register a new one by just creating a file under etc systemd system. And it's a bit boring, but like systemd has its own syntax for defining things, and this is where LLMs can be super useful, like just learning about what are the options. You can ask them, they will give you kind of like, they will teach you about this dedicated syntax, but kind of the TLDR here is we're telling our host Linux operating system, okay, whenever you start, there's this application, and please don't run it before the Docker service because it requires Docker. So the Docker service has to be running, and go into this folder and do Docker Compose app. And the -d is just so it like detaches, like it doesn't hang on the command line. And whenever someone wants to stop it, just do Docker Compose down. We start this service by just using the systemctl command line tool that uses this file in order to operate. So we can start the application. Looks like nothing happens. But if we look at the status, we can see that the same thing that we did before of doing Docker Compose app has been done, but now is the operating system that it's managing this. And we were to restart the machine, this will start automatically. And if we ping that same website, it's now back again running, and it tells us that it has been visited 4 times. And if we want to stop it, we just stop the service. Okay, the last topic I want to cover today is how you not only create these artifacts, but get people to access them. Like, so far everything is like you create this file, but where do you put this file? Well, you could put it in a website and just have people download it. And this, for example, what kind of the Ubuntu people do. This is just like you can download the files from here. But in practice, the common way of doing this is through, as we have been seeing, is putting them on GitHub. So a lot of packages will just put the code on GitHub and give you instructions on how to install it. In fact, package managers can install directly from GitHub. Like if we go, yep. So before we saw that we could do pip install requests, and that will go to the Python package index. But we could also have just say, okay, install from the latest version of the source code. And this instead just downloads the source code and will build a wheel from that and then install the wheel. We could also see whether request publishes wheels. Request does indeed publishes wheels. So we can grab this URL and do the same thing. In here, we're now installing, instead of from the latest, we're installing from this specific release, but it's just a file. As long as we can get it, we should be able to install it. Yet, you probably are wondering, is this where pip is going? Pip is not going here, whether pip, where pip is going, we can actually find by making it give us all the output and then filter for the wheel. And I think we have to uninstall it first. Yeah, there we go. So we uninstall it and then we install it again. And here we can see the exact URL that was used to get the metadata and then the URL that was used to get the package itself. And now the question becomes, how do I put my package in PyPy so other people can find it? While pip cannot help us with that, UV can. And if we go to greeting, we make sure that it's, actually not greeting. Greeting is taken, so we can go into missing semester just for demonstration purposes, and we can build the package. Now we have this wheel, and if we say UV publish, and when here we're giving this extra command, I'll explain it in a minute why we're doing that. We have now uploaded our wheel into the package index for other people to use. It will be a waste, just kind of polluting PyPy. So the Python developers came up with test PyPy, which is a replica of PyPy that you can use to just test that you know how to publish packages. So here, I think this was the previous version that I was testing, and what we just ran upgraded it to the next patch version. And since we give some instructions on how this is published, there's actually a README and people can use it. And if we go back, if we do UV pip install from test PyPy and the missing semester package, we're downloading, I think it's using the, it's downloading the package and unpacking into our virtual environment. The story is really similar for pretty much any package and even for other things like Docker. Like if we want to release that greeting Docker image for people to use, we'll first have to build it in a specific way. Docker will only let us push images that you have permissions over. I will only have permissions over images that start with my username. So we have to build it with that detail in mind. It's exactly the same image we built before. So there's pretty much a no-op. We're just tagging it as so. And if we now post this image, Docker, it's finding that all of this has already been pushed. But if we go into Docker Hub and we check, anyone can now go in and download this image, and they have like an entire file system to run this green app. Yep, and the exercises cover a lot of these patterns, and I think it's kind of a lot of information to go through. A lot of this you will learn by doing and like kind of building your own kind of pyproject.toml and your own like Docker file and like pushing and installing. But hopefully everything that we have covered today gives you like a good mental framework of how dependencies and how kind of modern software applications are like built and distributed online. And happy to take any questions. Yeah.
To chew on.
Yep, yeah, I know. It's.
I have a simple question. If I'm collaborating with somebody and I've created a virtual world or a container online, how does he get access to my container world?
So you have to use a container registry.
Container what?
Registry. So the same way I post this onto Docker Hub. Docker Hub is not the only container registry that it's online, but as long as both you and him have access to the same point, then you will like be able to Docker pull and Docker push, and that will have all the dependencies. And you will have to authenticate, you have to prove to Docker Hub or like the GitHub container registry or like whatever container registry that you're using. You have to prove that you are you and that you have access to like read the contents of that container, but then it will allow you to download the entire image and then run the application. And the same ideas applies to pretty much any framework. Like with PyPy, there are public places, and you could put them on GitHub, and as we saw, you can install them directly from here. But yeah, as long as you have like a common kind of like repository to push code or artifacts, then it's very easy to collaborate with one another.
Even within the container.
Yep. Mm-hmm. Okay. No worries.